Hello everyone, my name is Do-Yeon Kim and I am a research engineer working at Team 9 Corporate Venture of Samsung SDS in Korea. The research topics I'm specializing in are deepfake detection, image anti-spoofing, and image forgery detection. Today, I'd like to present on the topic of deepfake technologies and the ways to detect them. The title of today's presentation is, Can you trust what you see in the AI-generated cyber world? We'll start off with a simple quiz to check your perception as a prologue, and then move on to the definition of deepfake, and find out about the opportunities, threats, and solutions regarding the issues of deepfake. Lastly, we'll cover how to deal with deepfakes in real life as an epilogue. Is seeing equals believing? I warned you to be prepared to check your level of perception. Let's start off with a quick quiz. Take a guess on which image is of a real person. At the count of 3, 2, 1, let's find out the answer. The person on the right is real, and on the left is a deepfake image of a person. The AI-based image synthesis technology is so advancing that it's hardly distinguishable in the eyes of humans. Well, let's take a guess again. Here's another mixed set of real and fake images. As you can see, the AI models can create people of different ages, races, and ethnicities, and even consider the camera angles for realistic outputs. So, let's find out which ones are real and which ones are fake. Well, to me, it looks like the fake images look much more realistic than the real ones. Then what is real? The technological advancement is unbelievably fast, but its range of domains is expanding from not only human faces, but also to various animals, transportations, objects, and even satellite images. All these images on this slide are fake and created by AI. It's fascinating, but kind of scary at the same time, since it's so realistic. So then, what exactly is deepfake anyway? As many of you are familiar with already, deepfake is referred to the AI-generated contents, such as images, videos, and audios. It first emerged in an online community back in 2017, and the word comes from a combination of deep learning and fake. Deepfake in early stages were only about manipulating the faces of celebrities and public figures to say things that they didn't and act in ways that they haven't. Nowadays, however, the target range has expanded to include not only human faces, but almost everything. The technologies used to create deepfake contents are generative models, and mostly generative adversarial networks, which is commonly referred to as GAN models. GAN models are composed of the generator and discriminator, which are adversarially trained to create realistic outputs. A common way to explain the training process of GAN models is the competition between the counterfeiter and the police. The goal of the counterfeiter is to make realistic fake bills to deceive the police, and the goal of the police is to discriminate between the real and fake bills to stop the crime. The actions of trying to deceive and discriminate helps improve their abilities, and eventually the generator will be able to create highly realistic outputs that the discriminator cannot distinguish. In this way, the GAN models are able to create high-quality fake images. There are various generative models which can produce realistic fake images, such as normalizing flow, variational autoencoders, diffusional models, and GAN. As you can see, the images created by GAN model are the most realistic and advanced ones compared to others, because you can control the age, ethnicity or race, accessories as glasses, and even the camera angles. The abilities to enable such features are what differentiates GAN from other models. Overall, we can summarize them as 3 differentiators of GAN: The first is high-fidelity generation, which enables creation of realistic outputs in high resolution of 1024 by 1024 pixels. The second is controllable generation, which enables detailed control of features and attributes in fake images. In this way, we can generate fake images in the ways we want. Thanks to the controllability, GAN models can be also used for image anonymization and alteration as well. The last point is fast sampling, which enables quick and easy creation, which is a huge plus compared to other AI models when the same computing power is given. Let's take a look at each differentiator in more detail. GAN is first introduced by a famous AI researcher named Ian Goodfellow back in 2014. Although the outputs were relatively low resolution and grayscale images, it was a groundbreaking innovation for the fact that the computer-generated face images could actually look like human. Before GAN, it was highly challenging for computers to automatically place the facial features at the right location. Thanks to GAN making a giant leap in AI-based image generation, technologies have been continuously improved and evolved to reach a point where it can generate a realistic face with wrinkles, gray hairs, and even skin pigmentations as shown at the very right. In 2017, another famous GAN model named Progressive GAN by Karas from NVIDIA came out. Progressive GAN has enabled improved quality, stability, and variation of generated images by enlarging the pixel blocks from the size of 4x4 to 1024 by 1024. You can see how the image quality becomes noticeably improved as the resolution and the training time increases. In 2019, the famous StyleGAN was introduced by the same author of Progressive GAN, Karas from NVIDIA. StyleGAN is an advanced GAN model from generating realistic images based on style transfer. The results are, as you can see, highly realistic and diverse compared to other GAN models. In 2020, StyleGAN 2, the improved version of the previous StyleGAN, was introduced. The outputs of StyleGAN tend to contain certain water drop-like artifacts, as shown at the top right corner in the red circles in the image. They are all fixed now in StyleGAN 2, so as you can see, the results are almost flawless now. It's pretty amazing. The second differentiator of GAN models is controllable generation. Starting with the vector Z in the latent space, the generator generates a fake image. Then, by simply moving the vector Z to different points in the latent space, we can effectively control the attributes in generated images to change the age, accessories, or gender. This is a figure from StyleGAN 2 illustrating the image-to-image translation. The faces on the first and third rows are transferred as the style changes at the very left. You can notice how natural and realistic they look, even when the camera angles are tilted from the left to the center and to the right. It's so fascinating that it makes me watch over and over again. Here's another cool technology called mask condition generation, which enables diverse and interactive image manipulations. By manipulating the facial mask on the left, you can see how the original image in the center is transferred to a different style as the output on the right. It is simple and easy to maneuver, but the results are pretty realistic and high quality. This is also fascinating to add some bangs and change the eyebrows and enlarge the ear and the nose. Mask condition generation can be applied to not only human face images, but also landscape images as well. We can add in a tree and a mountain and switch the ocean to grass and even change the color of the clouds. I think it's fascinating that the AI model can generate high quality images from the very simple drawings on the mask. This figure illustrates a style transfer based on the change of vector in the latent space. So from the image on the left, we can add a pond, or change the sky to sunset, or the night sky with the stars. You can see how the grass changes too with different lighting conditions. Next, let's find out more about the opportunities using the advanced technologies for digital content creation. It is now possible to resize the small and low-resolution images into high-resolution quality images thanks to generation models with advanced upscaling techniques. By repeating the process of upscaling and downscaling, we can even restore the faded and deteriorated old images from the past to high-resolution images. Also, this technology is being used in the commercial market to enhance the quality of ultra-high-definition TV for video and audio quality optimization. We can also generate unique virtual characters with different personas using the technologies of generative models. Using the MetaHuman creator of Epic Games as shown in the images on the left, you can easily create virtual humans by simply selecting the race, gender, age, and expressions of your choice. They can be employed for various use cases, including a YouTube creator, a chatbot character, or even a virtual friend. When using the virtual humans, there's no need to worry about the privacy issues or even the risks of coronavirus pandemic. Recently, virtual broadcasters or reporters are also introduced to deliver the news in Korea. Using the natural language processing technology, AI news reporters can deliver the news non-stop 24/7 with the help of GAN models. They never get sick or tired and can be employed simultaneously to different programs and even deliver multilingual news at a lower cost than human reporters. The possibilities of GAN-based content are almost infinite. Next, let's take a look at some abused cases of deepfakes and the threats concerning them in the era of disinformation. Deepfakes are fascinating as it can be. However, advancement in vision technologies can become a serious threat to our society. According to Gartner's top strategic predictions, AI-driven counterfeit reality creates digital mistrust. Also, by 2022, the majority of individuals in mature economies will consume more false information than true information. With the flood of information we face on a daily basis, I think it might become a reality sooner than expected. Deepfake has become a security threat to financial industry as well. In 2019, cyber crooks stole cash of $10 million using a fake voice of a CEO. Just imagine if you received a video call from your CEO with his number, with his face, and his voice. It would be very difficult to discern whether it's the real person or not. What if he's in a rush and demanding you to wire transfer some cash to close a highly important deal as soon as possible? I think it might be more difficult not to transfer the money. Also, AI can be used as the newest weapon, the deepfaking photos of the Earth. As shown in the image on the left, fake satellite images, including non-existing bridges and roads, can be maliciously distributed to carry misinformation to the opponents as a military tactic. As I've mentioned earlier, anything can be generated by AI models in near future. They can be definitely trained as AI-enabled weapons as well. Well, recently, just early this year, there was a $76 million scam using deepfakes in Shanghai, China. Deepfakes were used to fool the face recognition system of the Chinese government for tax evasion. The prosecutors and police have arrested the criminal who made the fake voice by combining real personal information with deepfake faces. The criminals hacked the system using the smartphones and injected a deepfake portrait to pass face verification system. There are two implications discovered from the case. First, deepfakes can be used even for high-tech crimes. And second, we find a need for integrating the face recognition system and deepfake detection technologies. Another case from February this year was deepfake abuse for political purposes. A cabinet secretary, Mr. Kato, was reported to smile at the tragic Fukushima earthquake and tsunami, but it was found to be a manipulated deepfake image using the mobile application FaceApp. The picture spread out on Twitter with hostile comments within 30 minutes after his TV interview. Since it is so simple and easy to create deepfakes on smartphones, proactive corresponding is important and required. This case was found in an online review of a hair shop in Russia. One of our partners reported that a hair shop in Russia posted the online reviews with deepfake profile pictures. Adding pictures bring more reliability than just plain text, and using deepfake images can help avoid privacy issues. This case shows how deepfakes are becoming a part of our ordinary life so quickly. Next is the case of Katie Jones on LinkedIn, a Russian LinkedIn user based in Washington, D.C., United States. She was a 30-something intellectual who had a prestigious job at a top think tank organization and made various powerful connections close to the U.S. government officials for critical intelligence. However, Jones was detected as a part of online spy operations, and her profile picture was a deepfake image, as reported by the AP News. According to the director of U.S. National Counterintelligence and Security Center, foreign spies routinely use fake social media profiles to approach the target people. In May 2020, a retired CIA officer in the United States was sentenced to 20 years in prison for passing details of top-secret operations to a recruiter on LinkedIn, who was actually a disguised spy from Beijing. As shown in this case, deepfakes can bring severe consequences and even become a serious threat to national security. As mentioned earlier, deepfake satellite images can be abused as an AI-enabled weapon, as reported by Defense One, the military journal. According to the officials, China is leading in generation of deepfake satellite images to fool the experts with fake geographical information generated by GAN technologies. Defense Advanced Research Project Agency, which is known as DARPA, showed that such images can pass the recognition system, and the CIA was concerned about the threat. This case shows how deepfake can be a threat in a military perspective as well. Next, I would like to share some of the recent responses to deepfake threats. There are efforts brought together to minimize the risks and protect the society from the threat of deepfake abuse. For technical perspectives, the United States is the world leader in the technical approaches. Last year, in 2020, Facebook has banned the posting of deepfake videos and even deleted the suspicious posts with deepfake images and videos before the presidential election. Facebook also hosted the Deepfake Detection Challenge with Amazon, Microsoft, and others in 2020 to encourage fellow researchers around the globe to participate in improving the deepfake detection technology. Microsoft has led the deepfake distinction campaign also for the presidential election last year and organized the online alliance called the Reality Defender 2020 and provided the guidelines to deal with deepfakes. DARPA has funded a media forensics research project ever since 2019 to fight against the threat of deepfake abuse. For legislation perspectives, Virginia of the United States became the first state to outlaw deepfakes by adding the term to the current revenge pornography category. Also, Singapore has announced the Protection from Online Falsehoods and Manipulation Act in 2019. Those who create false information, including deepfakes, can be sentenced to 10 years in prison and also 100,000 Singapore dollars as penalty. Last year, Korea has also added the term deepfakes for the Sexual Violence Punishment Act to punish those who generate or distribute deepfake pornography. Next, I'll explain the technologies for deepfake detection. The approaches for deepfake detection can be categorized into three types: the frequency-based, image-based, and physiological feature-based detection. I'll explain each approach in more detail. First, for the frequency-based detection, we convert the images into frequency domain and utilize the differences in frequency components between the real and fake images. Due to the upsampling process of GAN models architecture, fake images contain the checkerboard patterns appearing in the frequency spectral. As you can see, the checkerboard patterns are quite distinctive in the fake images, especially those in the center, the cycle GAN, star GAN, and CRN. Our model also takes this approach because we found that it's effective to train the model in frequency domain for the purpose of preventing the overfitting issue of the model to certain object categories. By applying the Fourier transform, images can be converted from the image domain to frequency domain. As you can see in the image in the center, the low frequency components are located in the center of the image, colored in green, while the high frequency components are located in the background or the outer edge in the color red. If we transfer it into a 1D power spectrum in the very right, the high frequency components are located at the right side of the graph. We have conducted numerous experiments to analyze the difference between the real and fake images and found that fake images show a distinctive characteristics in the high frequency components. Just in case you can't see, here is a zoom in images of the real and fake images. The top row is a comparison of different categories such as human, face, cat, car, church, and horse. The bottom row is a comparison of different GAN models including progressive GAN, style GAN, style GAN 2, big GAN, cycle GAN, and star GAN. Unlike the graphs of real images, those of fake images tend to jump upward at the high frequency components. This means that the clues are hidden in the fine details in the outer edges, such as the texture of the hair or the background settings. Next is the image-based detection, which I previously mentioned already. Style GAN is a well-known example to contain the droplet-like artifacts in fake images, which are now fixed in Style GAN 2. In our own research, we have observed where the model is focusing to find the artifacts using a class activation map. As you can see in the right column, the model is focusing on the outer edges rather than the central region. So we can conclude that the artifacts in fake images are mostly found in the background. This is a technology called face X-ray, which focuses on the unnatural boundaries discovered in the face area. If you take a look at the image on the right, the facial boundary is noticeably distinctive. Lastly, the physiological feature-based detection analyzes the physical hints, such as the heart rate analysis and lack of eye blinking. The images at the bottom row show the blood flow measurement with light, and the difference is noticeable between the real image in the blue box and fake images in the red box. Another method is analyzing the facial landmarks to see whether the direction of the head pose and facial features align together. So we take a close look at the vectors of the red and blue and check the alignment. Lastly, I brought 3 examples of fake images here. Can you spot the hint? If you take a close look at the eye color, you can see how they're different. It is quite uncommon in reality to see different eye color for each eye, so we can use this characteristic for detecting fake images. Next, let me introduce Samsung SDS deepfake detection as a solution. Our deepfake detection technology uses frequency-based detection. My team started the research and development of deepfake detection in March of 2020 and has continuously improved the model since its first release in June 2020. Our engine focuses on detecting the generated images by GAN, ranging from the human faces to animals, transportations, and various objects. Our model's accuracy is over 90% with generalized detection ability, and our work has been published in a global AI conference in August 2021. Our next goal is to detect face swap and deepfake videos. Our work achieved state-of-the-art performance compared to other models. As you can see at the very last row in the bottom, our model shows the highest accuracy and average precision in non-training categories compared to other models. Well, let me introduce our anti-deepfake team of collaborators with Samsung SDS. To combat deepfakes, we have partners in academia, government agencies, startups, and the global companies, including Adobe. We've been working together with various people, especially the top-notch and high-class intelligent researchers at Seoul National University and Chunang University Department of AI. Here is our technical roadmap. As mentioned earlier, we have worked on the entire image forgery until the third quarter of this year, and now we're focusing on the detection of partial image forgery, such as face swap. Next year, we plan to work on the prevention of image spoofing on smartphones, such as utilizing the flashlight, which is our patent technology, and also expand the detection range to include deepfake videos and even the deepfake satellite images by possibly collaborating with the University of Washington and the United States. The last but not the least, let me conclude this presentation with the guidelines for how to deal with deepfakes in real life, as Microsoft presented in their campaign last year. Well, first, think about the potential impact with some suspicious media. If you've been sharing funny photos or memes on social media without taking considerations, try to search on the internet first, and you may be able to find the original versions of them. With just a little bit of effort and time, you may be able to find that it's not real. There are no general rules for identifying deepfakes, but when in doubt, try using our solution. If you have any more questions regarding our solution, you can always contact us for more information. Our contact email address is team9@samsung.com. Here is the picture of our team at Samsung SDS. We are all truly grateful for this opportunity to share the stories regarding the creation and detection of deepfakes. We're open for any questions or discussions or even some collaboration opportunities in the future. So contact us anytime at team9@samsung.com. So this concludes my presentation today. Thank you so much for listening.